Push that rock with Simpson math. Let's talk about exponentiation. We understand what a number to an integer is. It just means multiply the number by itself this integer number of times. So e times a whole number. If it's a negative whole number, so if the integers go into negative land, well then it just means multiply the reciprocal by itself that many times. We know that any non-zero number to the 0 power is 1. We know that these fractional exponents mean to take a root. So something as complicated as this, well, that would be e to the 314 hundredths. So we're definitely taking the 100th root. So we have the 100th root going on. But we're raising e to the 314th power. So you can do it in either order. We could take the 100th root of e first and then multiply that number by itself 314 times. But what does e to the pi mean? That's never been defined in any of your previous classes. I mean, pi can't be written in decimal form without that and terminate or repeat. In other words, it can't be written as a fraction of integers. So what does this mean then? It hasn't been defined for you. So think about the consequence of that. You know, we're used to graphing a function like y equals e to the x and just drawing this nice smooth curve. But can we? Because there's all these values, like at pi, there wouldn't be a value, and at square root of 2 there wouldn't be a value, and square root of 3 there wouldn't be a value, and square root of 2 plus 0.01 there wouldn't be a value. So is it just a disconnected bunch of dots, a dot for every rational number and an open dot for every, and just a space for every irrational number? So is it just a cloud of dots? Well, no. Turns out this is always continuous. It does just smoothly go like this. So no, y equals e to the x is always continuous. And the reason why is because the correct definition for an exponentiation is a infinite polynomial. So for e, the infinite polynomial looks like this. It's 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so forth and so on forever. And of course, there's a limit involved here. So if I want to know e to the pi, I go 1 plus x plus pi squared over 2 factorial plus pi cubed over 3 factorial plus pi to the 4th plus 4 factorial, and I keep going and going forever. But there is a limit that this will approach, that this polynomial value will, oh, I should have put a pi here, sorry. A pi replaces all the x's, otherwise it'd be variable. And this value, this sum, this infinite sum, adds to a number that's approximately equal to 2 pi. And on the graph, it goes exactly where you think it should go. You know, that's going to be e to the pi, which would be, you know, something like 23, I guess. But it goes exactly where it should go. So it turns out the graph is nice and continuous. It's a polynomial. Polynomials are continuous. So that's why the exponentials are continuous functions, and that's how we define exponentiation when the exponent is any number. It just turns out that e squared is equivalent to e times e. If you do this definition, it's 1 plus 2 squared over 2 factorial plus 2 cubed over 2 3 factorial plus 2 to the 4th over 4 factorial plus go on and on and on, and that will equal e times e, the same value. How about that? Now, we're going to talk about the differentiation rule for e to the x. I call this the give birth to the mother rule. Why does it have such a, admittedly, almost disturbing name? Well, normally when we take the derivative of a function, we're performing an operation. I mean, derivatives are operators, just like square roots or multiplication. And normally when we perform this operation, we get out a different function. You know, just like taking the square root of 16, you get out a different number, you get 4. Okay, that's what happens when you operate on something. What comes out is something different. It's not unlike an operation that happens in a hospital. You go into the hospital and you have an operation and you come out different. If you have an appendectomy, well, you come out without an appendix. Okay, so you come out slightly changed. So notice this 2x is still a polynomial, just like the function that was in here to begin with. X squared is a polynomial, so it's very similar, but it is obviously also different. This was a parabola, this is a line. So that's kind of what you expect when you do an operation. You expect something different. Imagine giving birth to a baby. When the baby comes out, here's the baby, here's the mother. You do the operation on the mother, and here's the baby. And look, it's different. Oh, it's kind of cute. It sort of looks like the mommy. It's got some similarities, but it's different. Okay, now imagine you wheel the mother into the hospital and you do the operation on the mother, and she's up there in that chair and she's got unfortunately her legs spread open in the stirrups. I mean, I've been in this situation several times. Many of y'all are maybe too young for this, but I've had 3 daughters give birth. I've been with my wife when she gave birth to my 6 children. So it's a fact of life. And so you're expecting this baby to come sliding out. But what if the baby, just as it comes sliding out in shocking form and looks not like the mother, a small version of the mother, but the mother keeps coming out. Like the mother is a 5-foot woman, and out comes a 5-foot woman that looks exactly like her. That's what happens when you take the derivative of e to the x. You get out e to the x, as shocking as that is. It's shocking. The derivative of e to the x is e to the x. What does that even mean? Well, what it means is that anywhere on the curve, e to the x, anywhere on this curve, e to the x, if you evaluate the curve at some value, you get out e to the a, and you want to know the slope, well, guess what? The slope is also e to the a. The slope at a of the curve is equal to the value of the curve. How surprising is that? Well, it's the only curve that has this property. It's very surprising. So that's the give birth to the mother rule. Kiddos, math made simple. It's Simpson math.